Alright, time for another DraftScience video presentation. Yeah. So I did listen to one of the Feynman lectures. I'll leave a link below to the audio files for actual lectures he gave at whatever, Caltech or something. Anyway, which are sort of interesting. So, yeah, there's about 50 of them or 60 or whatever, so it's a lot. But anyway, eventually I'll go through them. So this one was on the specific of conservation of momentum, and you can also just get the text of the lecture. Pretty much, it seems close enough to accurate. And I'm scrolling to get to so this is the air track explosion experiment. And so it's the same basic idea as what's in the Lewin experiment. There's a little, catch to this one where the explosion sends two carts of the same mass away, and then one of the carts hits another cart of the same mass to double its mass, and then it moves off at the half the velocity. And the argument I would make is it sort of illustrates that you just can't make any sense of this. So somehow the explosion works when they're equal masses. So when the two masses on either side of an explosion, the explosion gets the energy into the cart. And it's when somehow, logically you're saying, okay, so then the cart hits another cart and sticks to it, and it becomes a two-mass object, and it goes off. And now it's lost half its energy. So by the kinetic energy theory, half the energy is lost just by the one cart hitting the other cart. So I've sort of explained this in the sense that they have another experiment where they just drop the weight on a cart. And it's clear that it's half the velocity. There's not some other number, so it goes half the velocity. By momentum standard, momentum is just about completely conserved. There's so little losses. The number is a tiny bit smaller, right? The velocity is a little less than half the velocity, okay? Indicating this, there's some losses, but they're tiny losses. Yet kinetic energy says, I lost half the energy, just disappeared. I didn't move anything, I didn't heat anything, I didn't do any of those things they say. I didn't deform or deshape or, heat or in any way dissipate the energy into the environment. I didn't make a ton of sounds, I didn't do all that stuff. Didn't move a whole bunch of atmosphere, all of this other garbage, to account for half the energy of the system being lost. And so to me, this is a pretty compelling argument that something's wrong with this kinetic energy theory, that you can just say, all right, that just doesn't make any sense. Okay, it doesn't make any sense because if I put a two-mass object, okay, a one-mass object, and then I do the exploding thing, it goes half as fast. It conserves the momentum, and so you can't use you can't blame, you're not banging two carts into each other, so you can't use that as an excuse for half the energy being lost. And so now you have to blame the explosion. Somehow the explosion can't make the energy go into the heavier object. It just lacks any kind of making sense. But yeah, there's nothing new in the Feynman statements. They're all the same kind of arguments. They just evade having to deal with this huge kinetic energy loss and explain how this has anything to do with Newton's third law and principle, because, yeah, you conserve the momentum, but you completely destroyed a ton of energy, and there's no accounting for that. How can you say there's equal actions when you're clearly saying twice as much energy went this way as went that way? I just keep putting a lighter bullet in the gun, and somehow I'm deriving more energy from the explosion. And the heavier the bullet, the less energy I derive from the explosion. It's kind of like saying I exploded a nuclear bomb underground. I somehow made the bomb less explosive. It didn't have the same energy, even though it's obviously moving a lot of rock and it's melting rocks. It's doing all kinds of things. It doesn't make any sense. It's an explosion. Its energy has to go somewhere, and there's no accounting for where it went. And so it's just not very logical. So anyway, so the point I would just reiterate is that it is curious, interesting. It triggers the brain to say, wow, that they haven't done this simple experiment. Just putting two different objects on a spring and shooting them and seeing if the spring only produces 1.4 the energy in the lighter object for whatever reason, to make them equally energetic, to force that to happen. And it's just hard to believe that this experiment hasn't been done, that nobody's ever taken these carts at these velocities and proven essentially that the 10-ton train going 5 miles an hour has half the energy, that it lights half the number of light bulbs. I put a little generator on the train wheel, and this could be done with scaling. You can scale it down to any size. It's just the idea of extracting the energy and seeing if it's true that the faster object has more actual energy, that it's able to light more light bulbs. So we have absolutely no experiment. We could just go to it and say, there's kinetic energy proven. Here's the experiment, proves it, done. Nothing. And they're not difficult experiments, frankly. And it's just really bizarre. So, what I figure maybe I'll do is I'll just play my 15-minute video and point out how I can improve it. Because there's so much that you go through all this stuff, the bad history, the lack of evidence, these simple experiments never being done. It's just why isn't there? It should be in a video somewhere in the lecture. Richard Feynman should have said to people, hey, this is really curious, springs really don't work. They don't do this half thing. If I use a spring instead of an explosion, somehow the spring won't be able to produce these results. Okay, because the faster thing, the lighter thing, has to go away at 1.4 to make that energies equal. It doesn't, it just doesn't make any sense. So, well, anyway. So I think that's what I'll do. I'll decide while I'm paused. There's no comments. There's no links to any videos. There's no links to any lectures. There's no links to any arguments. There's nothing. Nothing. I could just repoint out that the whole mathematical derivation is just a perversion of Newton's mechanics, not anything reasonable. In the sense that Newton said energy essentially is force, and force is essentially momentum. And so if you change something's momentum, you can figure out by the change in the momentum how much force there was, because the force is what changed the momentum, because force is momentum. So anyway, we'll move on from here. This is strange. It's a strange planet, and strange beliefs, and strange ways of arguing, and it's just strange. Alright, I should be back, so we'll play some of this.
Another Draft Physics or DraftScience here on YouTube video presentation. I'm going to try to make this as brief as possible on the subject of energy generally, more specifically the distinction between the types of ways of measuring it, momentum, versus something like kinetic and potential.
Alright, so as I pointed out, I guess what I'll reiterate in the new version of the video is they have no model of the transfer. So I've gone to the trouble of drawing it many times, but you can understand the volume of momentum. Momentum gives you a mass platform, and then you're really just saying you're going to put a volume of velocity on top of it, right? And so the total momentum is just going to be the volume. So the smaller mass goes faster, the bigger mass goes slower, because less velocity, can be applied. But that's what you're applying. That's the P. That's the energy. It's just a volume. So the more mass you have, the less distribution of velocity you can have on the little mass bits, like they're little bits, And that's just the way it is. So there's lots of analogies, but you're basically spreading the velocity on the amount of mass. And then also in the interaction phase, they don't have any explanation for this energy transfer. In the sense that there's not intrinsically more energy, because it is all just going to come down to mass and velocity in the end. And the only way you create energy as heat or anything else is by either increasing the number of things you're throwing or increasing the velocity of the thing you're throwing. But that's the only way you make energy, and it's the only way it's distributed. And so you can sort of understand, if two equal objects bang into each other, they can just transfer their energy. But if one object's going a certain velocity and it hits another object that's not going any velocity, you kind of know, well, if it's going 30 miles an hour, it can't give it more velocity than it has. So if it's half the mass, the problem's going to be the thing going 30 can't give the smaller object any more than 30. That's all it can give it. It can't give it any more energy. It can only push it as fast as it's going. It can't push it faster than it's going. You can't hit it and make it go faster than it's moving. And then you have the inverse circumstance where the small object has to move a gigantic mass, and you can just sort of understand that it's to move the mass, it's got to move all the atoms, and that's going to, the more atoms there are, the more time it's going to take to get the energy to all those atoms. And the fast little thing isn't going to spend that time. It's it's moving fast, and it doesn't have time to wait for this reflection inside and all this other stuff that might cause it to leave. The energy is going to go in, and it's not going to hit all the atoms. It needs time for all the atoms to decide whether they're going to go. It's this all or nothing argument. You can sort of understand that the object if the object's going to move, all the atoms have to decide to move. If all of them don't decide to move, then it's not going anywhere. They all have to gain the velocity. It can't just half the matter leaves and half the matter stays. So that's clearly a deciding factor in how you can transfer energy from fast little things to big fat things. And I would argue that you could make a simple argument that what's really happening is the energy just reflects, because you can't move all of these atoms with this tiny number. So you can't distribute enough energy with enough area in the matter to move the entire thing. Even the size is going to matter, because you're hitting one little spot. You're not even affecting these atoms right away. But you can't move it. So what's going to happen is the energy is going to reflect inside of it, and it's going to come right back, and then you're just going to have this against that, which always creates just a reflection. So, But anyway, I've been through all that. They don't have a model. They can't explain where this energy goes. They can't draw you a picture of, you drop the weight on the train car, where half the energy is consumed. They'll not draw you a model of where it went.
Energy. Physics has two elemental simple equations, mv equals, and this more modern 1/2 mv squared ways of measuring.
Right, and it started as mv, so squared, let's understand. It didn't have the 1/2 in front of it for 130 years. So it was way off as an answer.
They call energy, this would be kinetic. This would be in newtons, this would be in joules. Simple translation would...
Right, the simple translation, again, another experiment never done is just to measure how much a stick of butter weighs after it falls 1 meter, because that's the definition of a joule. A joule is a newton falling 1 meter. So it's an average apple falling 1 meter. What's the impact? What's it weigh? That's a joule. And they've never done that experiment.
B is this...
I mean, never done it in the sense there's no link anywhere on the internet that I can find that shows that simple experiment.
Joule is 1/10 of a newton. Just to break it into a simpler context, And the fact is depending on how you look at two.
So that's just wrong. 1/10 of a Newton wouldn't be right. So the joule is going to be the Newton falling a meter, and it's going to, I'm guessing, somewhere around 2.3 is the right answer, actually. But we won't know till we actually measure how much a stick of butter weighs, how much it bends a spring when you drop it on a spring, how much does it compress the spring, how much does it weigh. And that'll give us the answer of how much a joule weighs. And the fact that they've never done this, it's overtly part of their, it's the very description of their unit. How you explicitly, the definition of a joule is the energy required to lift, 100 grams, 1 meter, 103 grams, something like that. And how much energy it takes to lift it is exactly the same amount of energy gravity uses to throw it down. So the answer is, how much does it weigh? That's the answer. That's what a joule is. It's a weight. And the fact that they've never even done that simple conversion.
Things that have the same momentum can end up having different kinetic energies, and even in circumstances where there is no potential energy or any other influence. So physics basically accepts having two fundamentally different answers, two different specific answers that can vary dramatically, hundreds of percentages in terms of being.
Yeah, even more, like the bullet example. Okay, the theory is that the gun and the theory is that you're supposed to have an action and an opposite reaction. Kinetic energy theory says the action of the gun is 4 joules of energy. The action of the bullet is 2,000 joules. So the bullet can do 2,000 joules of damage to the universe, and the argument is somehow the gun can only do 4. And somehow this has something to do with conservation of anything or Newton's third law, when it clearly doesn't make any sense at all. Now that example has existed for almost the whole 300, yes, for the 300 years. They've had guns for 300 years, I think. 2 something anyway, whatever. So what sense does this make? How can you have a theory where we'll just not talk about kinetic energy when we're talking about Newton's mechanics, because it doesn't work then. So the rule is, it doesn't make any sense again. Why talk about these equal and opposite reactions when they're clearly not equal and opposite? Now the fact is that the same energy will generate the bullet going. This magical 2,000 joules will be created by the same energy that's pushing the gun. So there's no doubt about those certain facts. Well, there's plenty of doubt. Plenty of doubters. I don't think there's any evidence to justify the doubt that if I did this in space, if I shot the bullet out one side of the spaceship and I throw the 2 kilograms 1 mile an hour out the other side, that I will continue navigating a straight path, because there will be an equal amount of energy.
Not the same. So the simple argument I would make is all energy is, a joule is moving an electron a certain amount of distance in a certain amount of time. That's energy. The truth is, it doesn't really matter at the time. We're just talking about moving. We're just talking about the fact that material things move in space.
So a more elemental unit of motion would be a force bit, for example, a piece of light, a piece of some kind of the energy moving at the speed of light. And there would be, you could say a joule would be a certain amount of that force moving a certain distance at and it's at a fixed velocity, the speed of light. But yes, for most cases, just measuring the momentum of an electron is enough to say a certain amount of electron motion will equal one of these joules.
It takes energy to move them. And I would argue that the space is really just made out of 2 things: the energetic bits, the bits moving the speed of light, and the matter bits, which move where the force forces them. So energy is best understood as there being 2 kinds of things in the universe, force and matter, and it's just the interplay between.
And the force is little bits with momentum, so it's just momentum. passed on to some other object that will have momentum, passed on to bigger objects that will have momentum. Everything is just momentum. And it works. It's reasonable. It fits.
The force and the matter. Where the matter is tells the force where it's going to be reacting, and it's really just a matter of the force has energy. It moves. When it interacts with matter, it moves slower while it moves the matter, and that, in essence, is the interaction between force and matter. So force is consumed by matter moving, and we call that energy. And we more specifically recognize when there's imbalances in force, that is, there's more force on one side of an equation than there is force on the other. That's when we say something has energy, because it's going to lead to there being movement in matter when there's an unevenness in the force that the matter's existing in.
So the argument is there's plenty of stuff called energy, that is motion in the universe, or momentum, but the only parts of the momentum that we find interesting enough to call energy are the parts where there's a differential between the pressures, the amount of momentum. Then we say it has energy, or potential energy. It's because there's a difference in the strength on one side versus the other side, how much light there is, for example.
It comes down to, it's made the most illustratable by a simple scenario where you have two objects. One object has half the mass and has, in theory, this one would have half the mass, and this one has 1m, and they have different velocities proportional to that difference in their mass. So this one would have a higher velocity because it has less mass, so we could say it had a velocity of 10, and this one would have a velocity of 5. Now these two objects would be described as having equal momentum, okay? mv on both sides is going to be the same.
So clearly I could have drawn this better. I could have made the bigger object, the more massive object, bigger, just to illustrate it more completely. This is a half I'm using. I should have used better numbers. So I used 5 and 10. I should have used 10 and 5 for the velocities to show the inverse relationship.
And it's their momentum as a measure. But if we use the modern equation of 1/2 mv squared, we'll see that this object has twice as much. This object going faster, the lighter object, the faster object would end up having twice as much. So if this number was 100 in momentum terms, their equation says it's 200, and the other object is only 100. It only has the momentum factor. Obviously, I'm saying that's just nonsense. This energy can never be recovered. So they say there's 200 joules. They say there's more energy.
So there's really just no experiment where they show you this inverse relationship between mass and velocity, and show you an experiment where the lighter, faster object does more work, produces something called evidence of the fact that it has more of these joules of energy. It has more of this capacity to make change in the universe. There's no physical experimental evidence of anything of this ever being proven. It's just asserted.
They'll never find an experiment where they can actually extract that extra energy. They're only going to be able to extract this energy from any experiment that collects energy completely.
So the 8-pound bowling ball going twice as fast than the 16-pound bowling ball, they're not going to produce an experiment where they show you that the 8-pound ball going faster somehow gives more energy to the pins. The total energy in the pin, box. That no matter what box I throw those two things into, I can't make more velocity and mass moving than what I put in. If the bowling ball comes to a stop, it gave its energy to the pins. The pins can only have the amount of momentum it has. It can only have the amount of mass moving at a velocity. There's no experiment where they show you that because it's moving faster and it's lighter, it's going to make more energy.
So that's the catch, is there's lots of different ways to try to capture something's energy, and some of them leak. You lose some of the energy in the process of attempting to capture it. But if you do have an honest experiment that captures all of the energy, these two objects contain exactly the same amount of energy. That energy is something you collect.
That's just my assertion in counter to their assertion. So they're asserting a different fact. I'm asserting that there's no evidence that they have different. And every bit of logic says they have to have the same, because why do we bother with Newton's third law if they don't? Because we know the same event is going to create both objects. That experiment I can show you. I mean, that's the Lewin experiment, okay? The one mass here, the two mass here, and whether we use Feynman's explosion or we use, Lewin's spring, doesn't matter which one we use. We get the same result each time. The half mass object goes twice the velocity, and the more massive object goes half the velocity. And that's just it. That's the truth. That's not fooling you.
So when falling in gravity, you could understand it as basically just being, you have a bucket and the gravity comes down at a certain rate, and it just matters how long you have your bucket in the gravity. It doesn't matter how fast you're moving your bucket, which way you're moving your bucket. The fact is, it's just how long is your bucket exposed to the
So all of this happened because of gravity. So I guess I should make that point, that this whole theory was created because of the fact that gravity it's thought of as if it's this force that affects everything equally. And it's exactly the opposite. It affects everything unequally. It gives smaller objects, it applies less force to them. Lighter objects, heavier objects, it applies more force per second. More stuff falls in the bucket per second. The bigger the mass, the bigger your rain catcher. And that's all it is. You're just catching wind. You're catching rain. And gravity is a wind. And you catch more of it if you have more mass. And you catch less of it if you have less mass. So it's giving you very uneven amounts of force.
Rain will tell you how much you collect. And that's the real definition of your energy, is what have you collected. To move the heavier object 5 miles an hour needs the same amount of little bits of pushers, okay, if it was weight or if it was gravity, as it takes to do this over here. There's no 4 times as much energy. There's no, all of that is just talk. It doesn't have any, there's no mechanical basis for it. There's no theory for any notion that because you double the speed of a car, say it's going 30 miles an hour and you double.
So again, this is back to the argument. They're essentially arguing that if you're pushing something, and let's say you're going to push at a speed that you're easily capable of running, so you're going to go from pushing something, 5 miles an hour to 10 miles an hour. Their argument is when their argument is you're going to push two things, one that weighs twice as much as the other. And their argument is that when you go to push the lighter thing, you'll only be able, using the same amount of calories of energy, you'll only be able to make it go 0.4 faster than the slow object. Only 0.4. You can't get it to, twice as fast. You're going to go 0.4 faster. So, what sense does that make? It doesn't make any sense to me.
With the 60, by their equation, it's saying that this car has 4 times the kinetic energy that this one has. It only has a doubling in the velocity. It's only got twice as much momentum. It only has twice as much energy. And if they do any honest experiment to detect...
Well, let's just say, I won't say the word honest, let's just say if they do any real experiment to detect, okay, they don't do any real experiments. They just do a bunch of, it's almost like hearsay evidence in court. They do these superficial, because we're like jelly, and jelly is affected by fast things more than slow things, therefore it's more energy. So we're back to the clay argument that because some mediums are more vulnerable to being disrupted or undisrupted by velocity. Velocity allows you to cheat in clay. Okay, clay gives an advantage to something going faster because it has less contact with the clay. It's pushing clay ahead of it, the whole thing. So there's an advantage to velocity in getting through some substances. I can make a cornstarch bucket, and exactly the opposite bias will be created. And cornstarch, I don't think that's right. What's this stuff? Um, well, anyway, I'll get exactly the opposite result. Okay, I'll get you hit it fast and it impedes your progress. You push into it slow and it'll let you go forever. So I could draw exactly the opposite conclusion about reality based on what substance I use to collect the energy. I mean, this should be something physics admits, that it has to be a little bit careful about how it collects energy because the method might have a bias. And we know that they do have I mean, it's an obvious bias.
The pushing power of the two vehicles, that pushing power will be exactly the same. It'll be exactly proportional to twice as much. It's only twice as much energy at 60 miles an hour, not 4 times as much energy. Twice is a lot. So obviously, and it's not, we as humans are hard. We can't judge how many joules are taking place based on what it sounds like or what it looks like. You have to test it with real science. If they tested it with real science, they would find that this duality of equations is just a non.
So friction happens more readily for slow things than for fast things. It's just a fact. So every interaction between two objects is radically changed by velocity. The faster I make this stuff happen, the differently it's going to happen. Just because the transfers of energy will be, for the faster thing, the transfers are all going to stay more in like a laser beam. They're going to stay in the same direction. For the slower thing, the transfers are going to get a lot more tangential to the initial velocity. And that's just a fact, a physical fact. They should acknowledge the fact and acknowledge that any perceptual difference between the half as massive object going 60 miles an hour and the twice as massive object going 30 miles an hour, it's just a perceptual difference. It isn't a real difference.
Sense that the 1/2 mv squared was poor science in its origin. There wasn't any convention that came to this conclusion. It was just a curiosity of history that it got popularized as a.
So yeah, the history is a really important part of it that no one will touch. No one will counter-argue any of the history except to say I'm a chauvinist because I pick on Madame Charlet or something. But they won't explain how she did good physics. They won't explain how there was any good arguments in the 1700s regarding this subject. All of the arguments on both sides were weak and sloppy, and none of it was good physics. None of it was well-founded. And the clay experiments are just such a huge example because you can just imagine there's all kinds of ways to mix clay. There's all kinds of clay you can find on Earth, and every mixture of clay will react differently. So you just select the clay for your theory, and you can prove it. Okay, so it's clearly not a very standard or scientific way to establish a truth.
Notion based on a couple of misunderstood experiments. It's just as bad as somebody taking the ferrocell or and drawing a bunch of conclusions about what magnetism is.
The depth of thinking that went into the defense of this kinetic energy theory is as superficial as Ken Wheeler's audience. I mean, it's that superficial. So these are, this is supposed to be science, and to not pay attention to, well, what's really happening? What's it look like under a microscope? What's this? What's that? What's that? None of that detail took place. They just went with superficial impressionism style experiments and didn't bother picking at it at all. Didn't even bother having a conversation about how clay has maybe a bias for velocity.
The experiments gave them a misimpression, dropping objects into clay, versus a more clinical way of capturing energy. Clay provides I can give you logical reasons why clay provides a bias to things moving fast. Fast things will go further in clay than slow things because the clay has time to react, to reflect, to stop slow things, and it doesn't have time to stop fast things, and that's all. It has nothing to do with how much energy.
It doesn't interact as well. It's just that simple. It interacts in a way that, like I said, the clay you push in front of you ends up doing the work for you, and it kind of gives you a free ride. So when you give something velocity in the same direction you're going, it's still your velocity in a sense, because it's still doing work for you in the direction you're traveling. So you don't have to do the work with what you have left. That part's doing it for you. The stuff you transferred is doing the work for you in the direction you're going. Obviously, if it starts doing the work in directions you're not going, then you're going to be in trouble, because now you're going to have to use whatever energy you have left to do the next push.
An object has, it just has to do with its penetration power, and that's a whole different measurement.
So I should use the laser beam analogy here because it's a good analogy. So when you scatter energy, you lose the capacity of that energy to keep penetrating. And if you keep the energy moving in the same direction you're moving, then it has more penetration power.
And it doesn't have anything to do with any absolute like energy. So it's clear that physics is just taking a terrible wrong turn with this equation. The original equation was just this mv squared part. I can still find modern physicists who are still just using this. They're not even putting a half in front of it. That's how much they really don't care about getting the right answer. I mean,
I can't say they're using it, but they're defending it as if mv squared had some rational origin when it doesn't.
Obviously, if you can have an equation, okay, and you call it, oh, we're going to tell you how much energy it has in joules, and then you throw a half in front of it at some arbitrary date. I mean, clearly you couldn't be taking your answer very seriously if you could cut it in half. If you didn't even realize.
So halfway in the process of the defense of this theory, they decide to radically change the definition and make their old answers 100% wrong, make them, way off. So the old answers they were defending as the truth became not true. And yet we're supposed to believe they got the right answer with the half thing. When they didn't care about what the answer, how accurate the answer was previously, and why should we believe they give a shit now? They still don't care about how real any of these answers are.
Realize you were half off, full 100% off, really. So I don't know if anything more needs to be said. It's just wrong. Momentum is the clear definer of your energy. If you have momentum, you have energy, you've captured real motion, and you have its potential, and you can transfer that motion. You can't transfer any more. You won't have 4 times as much because you happen to be lighter.
The relativity thing comes in here. Again, it's not about what your real condition is. It's just about your condition relative to the objects you're interacting with. And so it really doesn't matter whether you're going 40 miles an hour and they're going 60, or whether you're going 20 and they're going to. It doesn't matter where the energy actually is. It just matters on what's the difference between the two things that are interacting. And that's more reason to understand that this isn't about any kind of v squared thing, because then that wouldn't be true.
Going faster, lighter and faster doesn't give you any more real energy. It doesn't mean you can transfer that to anybody. You can't make heat out of it. You can't make anything else.
I'm just this small tiny bullet, just very, 1,000 times fewer atoms. It's 1,000 times fewer atoms to interact with the world. 1,000 times fewer, than the 2 kilograms. So of course, how much energy can there possibly be when there's 1,000 times less material bits, 1,000 times less soldiers, 10 soldiers versus 1,000 soldiers, right? No, 1 soldier versus 1,000 soldiers. That's a huge differential, right? So even if you make your 1 soldier Speedy Gonzales, come on, he's not going to have the power of the 1,000 soldiers who might be really slow pokes, but there's 1,000 of them.
So when they say this has 4 times as much energy as this, there's no rational explanation.
Sorry, 2 times. So my bad.
Well, twice as much.
Oh, I just said
these 2 objects, they have equal momentum. They're saying this one has twice as much real kinetic energy, and this. And, if they do a transfer one way, they'll say it lost, and if they transfer the other way, they'll say it gained somehow. This has a real kinetic energy.
So in here, I should bring up the fact that this creates a paradox. Either you have free momentum in experiments, or you have free kinetic energy in experiments. Just a fact.
But if I did transfer this one's velocity to this lighter object, the obvious thing is it will travel twice as fast away, and then I somehow made extra energy. It has more energy.
So the transfer would have to be through a lever. So if I throw the heavy object going, 5 miles an hour into one side of a lever, their argument is the other side of the lever can only produce 1.4. That means only 0.4 increase in velocity, even though it's at the point in the lever where the lever has to move twice the velocity. So I'm just, that's another experiment to do. Okay, pretty simple. I shouldn't do this, but I'm going to do it. Okay. It really is against the rules. So we just make a lever, okay, with the center here, so we're guaranteeing this is twice the velocity here, and so whatever comes in here gets doubled here, so it gets 2x'd at this location. So you just plow your heavy thing in here, okay, going just 5 miles an hour, okay, with a 10 mass, hit the lever, and the argument is this has to go twice as fast, and so we have the 5 mass object here, and their argument is no, this can only go 1.4, which is only 0.4 faster than this. It can, so it loses 0.6 of what it should be its added velocity. So it's pathetically slow. And again, they're making the same argument with like a bowling ball. You throw the 16-pound ball, and somehow if I pick up the 8-pound ball, I can only throw it 0.4 faster. Okay, that's how they're contriving the universe to fit their theory. And it's just, it's got to be intuitively, you got to be saying that can't be quite right. So this is the simple experiment also. Just send the 10 mass going the 5 velocity into a lever. Is that the way I want to do it? Yeah, the slow thing. Because now I can convert the slow velocity. See, I can't bang 5 miles an hour into something and make it go 10 miles an hour. But I can if I use a lever. Then I can convert this energy into energy out. And, the simple truth is this will leave at half the velocity, and not 0.4. And you'll convert all the energy here into energy here. It can't. Where's the losses? Where are you going to lose the energy? Where are you going to lose that 0.6? What are you going to use as an excuse when you have a lever? Where did all the energy go? Okay. Continuing. You can't have more. It won't have more in any experiment. You won't be able to extract it, by putting a generator on the wheel. Let's say you put a generator on the wheel, you'll generate just as much power, just as much real work capacity, okay, from this object as you will this object. They'll never be able to realize this 2x statement, that this one has twice. I suppose you could analogize this to football players, right? You could have the 300-pound guy going, 5 miles an hour, and the 150-pound guy going 10 miles an hour coming towards you. And you kind of got to know, which one you get hit by isn't going to make any difference. They're both going to have the same impact on you. The light guy isn't going to be twice as powerful. As much kinetic energy. They'll never realize it in a real experiment. So why wouldn't football players get smaller and smaller? If their theory were true, wouldn't football players start getting smaller and smaller instead of bigger and bigger? Because they'd have more energy, theoretically, because they could move faster. It would be all about how fast you can move, not about how massive you are and how big a problem you're going to be. How big so the theory, in a sense, is sort of proven by the fact that players don't get smaller, they get bigger. Yeah, this is probably enough. Anyone who is aware of physics and all the experiments should be able to understand that there should be agreement that the formula duality is evidence of a problem, even in itself. But the fact that these two formulas... So they deny the very fact that this was a replacement for Newton's physics. So they deny even the history all over the place. There was a real controversy. This was a replacement for momentum. This wasn't some argument that you keep both theories. It was clearly argued as a replacement. Momentum was wrong and kinetic energy was correct. It isn't some sort of, oh, this is a new way of viewing it where the two are compatible and all that. No, that had nothing to do with it.
Provide such dramatically different answers. Should be a pretty clear statement that this duality is a mistake, not some kind of fun feature. This isn't a fun feature of physics that you have two equations for defining energy. It's an error, and one of these is right and one of them is wrong, and I'd say all the evidence is this is the correct definition of energy.
Whatever evidence can be collected, again, and all of Newton's mechanics, well, as stated, most of Newton's mechanics isn't about collisions. So, that's the line you have to draw. It's about force interactions, and they don't have anything to do with kinetic energy, I guess. Technically, gravity isn't. The influences of gravity, kinetic energy wouldn't mean anything in terms of those pushes and pulls. So all of Newton's mechanics is sort of segregated from much of Newton's mechanics. Like I said, I don't know everything Newton said about collisions, but it wasn't much.
And this is just a nonsense of bad judgment 200 years ago.
Alright, so it really isn't that bad a video. I thought it was more explicit about the 10-ton train and 5-ton train, but no, it was more general, so that's good. So fundamentally not bad, but yeah, we'll plan on making throwing more arguments, especially the paradox argument needs to be emphasized, that this formula duality creates obvious paradoxes of creating free momentum or creating free kinetic energy, depending on which one you think is the dominant one in any circumstance. All right, it certainly blows up the third law, Newton's third law, if you take it at all seriously. Unless you're playing the game that momentum is somehow something real. There's no conservation of anything called energy in guns, for example. There isn't the same energy this way as energy that way. All right, by their definition of what energy is. Clearly, no equal and opposite reaction. So that's enough. So until we get more evidence, we're kind of just stuck. I just can't believe it doesn't exist anywhere. I mean, these experiments must be somewhere. Come on. Somebody had to have. Let's just see how far, how much energy there is in the spring. Let's put different masses on it and see how fast they leave the spring. But again, the complication there is like the Stephen Bro experiment. You have to know what your spring is capable of doing. You have to have a spring capable of moving as fast as the object is you want to push at a velocity. And if the spring doesn't have that tension to create the velocity necessary, then it's not going to be able to export the energy because it can't move fast enough to impart the necessary velocity. Anyway, so there's catches and you got to be careful and all that kind of crap. So, all right, so we'll call it a video, and like I said, over the next few days, I'm going to try to clean up enough to have enough room to do something, and then to see, like I said, I'll start with just weighing a stick of butter falling 1 meter. Nobody can do that. I mean, it's just so stupid that I have to do this experiment. Nobody else has done it or will do it. Just irritating. I'll have to make a scale, but scales are easy, right? It's just a lever again. You could argue, but if you use a spring, it's a little better. But yes, you just create a balance, and then you just know. I'll at least be able to say how many sticks of butter are in a joule. It weighs I'll be able to say it weighs 3 butters or 2 butters or 2.3 butters. Good enough. Anyway, till the next time and such. This has been a Draft Science, but you can't do science on the internet apparently. It's not viable as a subject. Very depressing.